Okay. Hello, we are live. Hello, everyone. I am Erin Broberg with Sanford Lab, and I'm your host for Deep Talks Pi Day. We are live on the Zoom webinar, and we're going to wait just a minute while we get connected to our Facebook live stream. So just hang in there for a second, and we'll get going in just a minute. Right. See our numbers rising. Thank you, everyone, for logging in. We're going to get started in just a minute as we connect to our Facebook live stream. Right. Hey, everybody who's joining, we're going to get ready to go in just a minute. Okay, looks like we're almost there. Just waiting for the go ahead. We'll be live on Facebook in just a minute. Okay, I got the thumbs up. So hello everybody on the Zoom webinar and hello everybody on our Facebook live stream. I'm Erin Broberg. I'm a communications specialist with Sanford Underground Research Facility, and we are here with our Deep Talks Pi Day celebration. So I want to take a minute right here at the beginning to thank our Deep Talk sponsors. We have Crow Peak Brewing Company, RCS Construction, Northern Hills Federal Credit Union, and Chuck and Jolene Lichtenwalner. We want to thank them so much for their generous gifts and their continuing support every month of our Deep Talks series. Crow Peak Brewing Company is sponsoring our door prizes again tonight. We have 3 prizes, and we're going to bring up the poll for our Zoom webinar viewers. This poll is only available for those who are joining us via Zoom webinar, so if you're watching on Facebook and you're missing out this month, join us next time via Zoom webinar, and then you can put your name in the drawing to win. So we're going to leave that up for a little while. To enter to win this prize, you do have to be 21 years of age or older, and you must be able to pick up your door prize at Crow Peak Brewing Company in Spearfish, South Dakota. We've got some great prizes. We've got a growler with 1 fill, a 6-pack of Crow Peak's locally brewed craft beer, and a gift certificate with a Crow Peak t-shirt. So if you're joining via Zoom, please add yourself. We'll leave the poll up for just another couple seconds, and we'll select the winner at the end of the event and contact our winners via email. So we'll close that poll in just about 5 seconds. Enter yourself if you're able to win that. Okay, and in the poll. Great. All right, so some of you may remember almost exactly a year ago when we were planning our 2020 Pi Day celebration with Dr. Travis Kowalski at the Sanford Lab Homestake Visitor Center in Lead. That was the first event that Sanford Lab canceled due to the COVID-19 pandemic. So it's been a year since we've moved our public outreach events to our virtual format. And we've learned a lot. Many of you have seen us learning even while we're live, but we've also been really surprised by what we've been able to accomplish. Last summer, we hosted a week-long Neutrino Day event. In October, we partnered with labs in the United Kingdom for an International Dark Matter Day celebration. And last fall, we took Deep Talks virtual. We've invited you underground with virtual tours of laboratory spaces, and we've live streamed to classrooms and to students at home. And we've reached a more diverse audience than ever. So tonight, we wanted to thank you, our audience, for making our virtual events a success. Thank you for continuing to support these events, for giving us feedback and asking questions, for sharing these events with your friends and colleagues, and for even hosting virtual watch parties, and even at times reminding us to hit unmute. We're so looking forward to safely hosting in-person events in the future. But for now, thank you for joining us virtually. Tonight, as always, we would love to hear your questions. If you're joining via Zoom, please use the Q&A function to submit those questions. And if you're watching live on Facebook, just pop your questions in the chat. in the comment section. To get started, we're going to introduce tonight's speaker, Dr. Travis Kowalski. Dr. Kowalski is the interim head of mathematics at South Dakota School of Mines and Technology. Each day, he helps the students there see the surprising ways that math intersects our daily lives. Kowalski has been awarded the 2014 Bernard Anega Award for Teaching Excellence from School of Mines. He has been recognized by the Mathematical Association of America several times, including the 2017 George Poya Award for his College Mathematics Journal article, The Sign of a Single Degree, and the 2019 Burton W. Jones Award. And in 2021, Kowalski was awarded the Distinguished Chauvenet Prize, which recognizes outstanding expositionary articles on a mathematical topic. And tonight, Dr. Travis Kowalski will discuss the many ways the number pi has shown up in history and culture. So please welcome Dr. Travis Kowalski. Thank you.
Thank you, Erin. All right. So let me go and take my mask off and share my screen, and hopefully we can get started. So let's see. That's a good deal. So we are ready to go. So like Erin said, my name is Travis Kowalski, and we're going to be talking about slices of pie, and not the fun sugary kind, the brutal mathematical kind. Oops, make sure my thing will advance. There we go. We're going to be talking about the history and humanity of this famous number. And so before we get started, I'm going to go and read kind of a favorite limerick of mine. "'Tis a favorite project of mine, a new value of pi to assign. I would fix it at 3, for it's simpler, you see, than 3.14159. And so this is going to be a talk of this number. The number pi, 3.141592653589793, and then more after that. This is a talk about this famous number, and we're celebrating it right now because it's so close to Pi Day, which is March 14th, which is the 3.14 part. This is actually not a discussion about pi itself, but about these approximations that we sort of have as part of our lexicon. So this is really a talk about the slices of pi, those little finite bits that we sort of know when we're talking about this number. Now, as Erin said, I was supposed to go and give this talk about a year ago, and then something came up. I don't remember. We had to go and reschedule, but we're going to go and do it now. So let me talk first about a couple of important slices of pi that folks know. So if you're a well-adjusted human being, then you probably know the classic 3.14 slice of pi. But depending on your degree, depending on your career, you might have to know a longer slice of pi. If you're a scientist, maybe you have to know 3.14159. If you're a mathematician, you might have to know an even longer slice of pi. If you're an engineer, there's a door prize for you. And if you're watching this tonight, well, I'm going to try to teach you 16 digits of this number by the very, very end of it. And so you'll walk away with, if nothing else, an extremely long set of numbers and maybe some interesting historical perspective along the way. So if I'm going to go and spend 40 minutes or so talking about this number and trying to get you to know the digits of this number, I should probably at least spend a little bit of time and energy talking about why it matters. Why would we care about this? So let me do that right now with part 0, a justification. So I'll switch into my professor mode here. The number pi is defined as the ratio of circumference to diameter of any circle in Euclidean geometry. The number pi is irrational, it's transcendental, and it's approximately equal to 3.141592635897932 and change. The number plays an essential role in many mathematical disciplines, including geometry, where it pops up in the equations of volumes and surface areas of objects that have circular cross-sections. It pops up in probability and statistics, in the formulas that govern the probabilistic distributions of normal and Gaussian distributions. It pops up in complex analysis, in the formulas that describe the interplay between complex arithmetic and complex calculus. And none of this means anything to any of you. This is the wrong way to try to justify pi. This is, I can justify pi if you believe those other things are important, and those other things are important only if you've spent years and thousands of dollars on a mathematics degree to learn that. So let me try a different tack. instead of trying to talk about the number pi in terms of its applications, let me focus on just the number pi by itself. And the story of pi actually has a very interesting, very simple starting point. The story starts off with circles. Circles are ubiquitous in nature. We find them everywhere. There are circles that are celestial in the sky above us. We live on a giant circle. Our days are illuminated by a big orange circle. Our nights are illuminated by a small silver circle. Circles are terrestrial and mundane. They're the path of an animal tethered to a pole. They're an irrigation circle in a field. And somewhere in the middle of this, the celestial circles in the sky and the mundane circles on the ground, they form the basis of art. They're a metaphor for things that have no beginning or end, things that repeat over and over again, things that are perfectly symmetric. And so it's not really a surprise to find out that circles pop up in the sacred art forms of a number of different cultures. And I've got a bunch of them illustrated here. There is the lotus circle, which is a Hindu symbol for life. There is the Chinese yin yang, a symbol for balance. There is the Lakota medicine wheel, a symbol for direction and nationality. And then there is the Pythagorean pentagram, which is a symbol for mediation, or if you rotate it slightly, for awesome hardcore death metal. There we go. So in all of these circles, this number pi is hidden somewhere in plain sight. And so that's really what this talk is going to be about. The story of finding pi's digits hidden inside circles isn't a story of math or engineering or science. It's a story of human creativity, of human ingenuity, and human technology. And every bigger piece of slice that we know, that we've learned about, that we've committed to memory, indicates some quantum change, some paradigm shift in how we as a species think about, write about, and talk about mathematics and numbers. And so it's a long story, and I'm going to tell it in 4 parts. 4 historical slices of pie, which you can kind of see up there in the color scheme, that come from 4 different cultures across 3,800 years, almost 4 millennia of human history. So if you're ready, let's get started. Part 3, the cradle of civilization. So when I say the cradle of civilization, I am referring to the Fertile Crescent. I am referring to the river communities that formed around the Nile and the Tigris and the Euphrates rivers. The Fertile Crescent is home to several of humanity's earliest civilizations, including the Egyptians, the Babylonians, the Canaanites, the Israelites. All of these societies created written languages, they codified laws, they managed agriculture and domesticated livestock, and more relevant to what we're going to talk about here, they developed practical rules for working with numbers and shapes. In other words, they built mathematics. So one of the shapes that they focused on were circles. And that might seem a little bit weird until you think about, we're talking about cultures who grew up around rivers. And so as I keep zooming into the planet closer and closer to a river, irrigation circles are one common feature of the landscape, and they go back thousands and thousands of years. So circles were just lying around for these cultures. And so let's take a moment as a side issue just to think about circles. Given a circle, there's 3 fundamental attributes that we can measure on a circle. There's the diameter. How far across does it take to measure the circle? There's the circumference. How long around is the circle? And then there's the area. How much space does that circle take up? And so the question, the mathematical question would be, how do these 3 attributes relate to each other? What connections can we make between them? Now, I'm going to put a pin in the area issue right now. We'll come back to it, don't worry. I'm just going to scoot it off to the side here. And we're going to focus instead on circumference and diameter. How are these 2 things related? And so I'm just going to have us do a thought experiment here. I've drawn a circle with a diameter going across. And imagine you were to have 2 people who are going to walk across the circle. And so one person is going to walk straight across while the other person is going to walk around the top half of the circle. And if I ask you, which of those 2 people took the longer trip? Folks in the audience here? Yes. The person who took the red path took the longer trip, right? The shortest distance between 2 points is a straight line. And so the blue distance is going to be shorter than the red distance. Now, if you were to repeat that when you walk back, the person who walked the red path actually made a full circle, while the person who walked the blue path did the diameter twice. And so without knowing anything more than just these facts, we can tell that on any circle, the circumference is always bigger than twice the diameter. Now, circles are related to squares, and so I'm going to actually go and redraw this picture and stick a square around my circle. And so I could ask kind of the same question. Imagine walking around this time the circle versus walking around that exterior square. So say I were to walk from the western point to the northern point, and I have two different paths, the path along the circular arc and then the path along that corner of the square. And it's kind of clear that the path along the square is the longer trip. And so if I repeat this over the next 4 sections of that circle, I'd find that walking one circumference is less than walking one perimeter of a square. Since the sides of the square are the diameter, that means that the circumference is smaller than 4 diameters. And so basic thought exercise, nothing terribly exciting, but we figured out that the circumference is always bigger than twice the diameter and smaller than 4 times the diameter. And so we could say, on average, the circumference is about 3 times the diameter of a circle. That's our first relationship. It's one of the oldest relationships known in mathematics. It's older than dirt, literally. Here is a piece of Babylonian dirt. This is YBC 7302 from the Yale Babylon collection. It dates to about 1700 BCE from around the Tigris. This is an example of a very old Google search, essentially. This is a cheat sheet for mathematics. For these cultures, paper hadn't been invented yet. And so if you wanted to write something for posterity, you would go to the river, take some of the clay from the riverbed, and then use a reed to sort of etch in what's called cuneiform, the Babylonian alphabet. And then you would leave that thing to harden overnight, and you would have essentially some file that would never, ever, ever decompose. We've got thousands of these things. And so what we have is essentially history's first handheld tablet with stylus. So what does this particular handheld stylus or tablet tell us? It tells us that the circumference is about 3 times the diameter. And if you're not up to speed on your ancient cuneiform, let me help you out here. This is actually a circumference problem. And etched on this, you can see a circle etched through the middle there. That's the circle. The problem is asked to find the circumference of the circle. And etched right along the upper edge is the number 3. And then the rest of it is the calculation of taking the number and multiplying it by 3. This is the oldest written proof of evidence that we have that the circumference of a circle is about 3 times the diameter. But it's not the only one. If we were to go over to a different river, the Nile River, this is a papyrus from the Egyptians. It's called the Ames papyrus or the Rind papyrus. It dates to about 1550 BCE. It's largely a homework set about triangle problems, but there are a couple of problems on here that involve circles, like this particular one right here. And again, if you're not up to speed on your ancient Egyptian, this is a problem that says, if you know the square fencing around a circular field, to figure out what the circular fencing ought to be instead. And in the supplemental solutions guide to this, the author, Ames, who wrote the solution guide, said that the circumference of a circular field was 3/4 the perimeter of the square. That's a different phrasing, but since the perimeter of a square is 4 diameters and 3/4 of 4 diameters is 3 diameters, this is the exact same statement. The circumference is about 3 times the diameter. You can even find this in the Bible. If you were to go, and actually it's in the Bible in a couple of places, but if, for example, you were to go and pull out your King James Bible and flip it open to 1 Kings chapter 7, verse 23, this is a description of some of the things in the Temple of Solomon. He made a sea of cast metal, circular in compass, measuring 10 cubits from rim to rim, 5 cubits high, and it took a line of 30 cubits to measure around it. And so if you focus on the rim to rim part and the 30 cubits around it, you've got a statement that says that the circumference, the 30 cubits, is about 3 times the diameter, 10 cubits. I bet you didn't know that there were historical math problems hidden inside the Bible. So these are 3 ancient examples. Before we go on any further, I want to point out that you can actually experiment with this on your own. If you go to the website, there's an activity, there's a set of 3 activities that you can download. And one of them is a chance to experiment with this idea using circles lying around in your own house. And actually, I'm going to do this over on a side table here just to kind of show you the idea that the diameter of that the circumference of a circle is always about 3 times its diameter. So if you'll join me over to here, do I need to unshare? Oh, perfect. So I'm over here at this table here. This is my cool stacked periodic table of the elements, but all you need is just a bunch of circles to play around with, some kind of a rope or a string, some kind of scissors, and some kind of marking instrument. And so what I'm going to do is I'm going to take one of my circles, say this circle right here, and I'm just going to take the string and wrap it around the circle exactly once. So as I work my way around, there's about where the circle wraps, or the string wraps around the circle exactly once. And I'm going to take my scissors and cut this. And so this piece of string right here is the length of a circumference. And I want to compare it to the diameters, which means I can just lay this against the circle I've got here. So if I take one end of the string and I put it to one side and I mark it across, this is approximately 1 diameter's worth. And so I'm going to take a pen and mark it. If you were using, say, a ribbon, you could actually go and color this entire segment in. But I've got this little silver mark right there. And then I'm going to take that silver mark, bring it to the end, measure the string across one more time. And so I'll mark this again with this point right here. So marking this with silver. And then I'll line it up at the side, pull it apart across one more time, mark it at the very, very end. And at this point, each one of these silver marks has been exactly 1 diameter. So this length up to this silver mark right here is a diameter, up to this mark is another diameter, up to this mark is 1 diameter, and then I've got a little bit of change here. So the circumference is about 3 diameters worth. Now, that's just one circle. I could repeat this on a smaller circle, and that's the important part, is no matter what the size of the circle is, if you were to go through and measure one circumference around it, so one full wraparound, and so that's right here. I will cut it off with my scissors. And this time I'm just going to eyeball it. If I were to take this chord and compare it to diameters, I could measure it across here, and I would have about 1 diameter here. I'll use my finger just to pull it apart. I'd have a 2nd diameter here, pull this apart. I'd have a 3rd diameter here, and I'd have a little piece of extra. So no matter what the size of the circle is, the circumference, the length to wrap around it, is always about 3 times the straight distance across. All right, we'll come back over to this side right here. And so, what does all this have to do with pi is probably a good question. This is a Pi Day talk, and I'm doing arts and crafts over here with circles and markers. What does it have to do with pi? Well, we've just found out that the circumference of a circle is about 3 times its diameter. There's got to be some number where the circumference is exactly that number times the diameter. Based off of my string, it's got to be about 3 and change, a little bit longer than 3. And so there's some value that will make this almost equation into an equality. Since the Greek word for circumference is peripheria, and the first letter in that word in Greek is pi, that's the symbol we've chosen to denote what this number is. So we know the circumference is approximately 3 times the diameter. The number who makes this in equals is called pi. If you want to be more formal, I can put on my formal professor hat and say, pi is defined as the ratio of a circle's circumference to its diameter. But that's just this equation right here. And so the work we've got from these 3 cultures of antiquity has shown us that pi is approximately 3. And so we're going to call this the first slice of pi, the historically most ancient slice there is. Now, a question that you might ask is, all of us tend to walk around with knowing pi to the nearest 100th, 3.14. These are cultures who built the pyramids. They gave us Hammurabi's code. They have aspects of their culture that have survived to this day. Why didn't these people have a better estimate for pi? And the short answer is because the estimate they had worked. These were people who viewed mathematics as a tool. It wasn't anything different than a plow or a hoe or a shovel or a brick. It was what was needed to get things done. And so as long as it was good enough for the problems they needed, good enough or close enough was good enough. So it would take a long time for an advancement in understanding what this number was to occur. And that advancement would have to wait until we had a culture that had a richer idea of what a number was, that numbers were things you could study, not just tools or adjectives, and who approached mathematics from a logical point of view instead of from an empirical, well, it kind of looks like it works point of view. And we're not going to find that culture in the Fertile Crescent. Instead, we're going to go and have to look across the Mediterranean Sea up to Greece. So let's talk about the Greece. Part 3.14, Greece. So we owe an awful lot to the ancient Greeks here in Western civilization. All of the traditions that we associate with that, democracy, rational thought, philosophy, history, medicine, these all owe themselves in the way that we understand them in the United States to the Greeks of antiquity. In addition, they unlike the Mesopotamians, who were viewing mathematics as a practical tool, the Greeks viewed mathematics as an ideal, something you aspired to. The math wasn't just something that described what you saw. Mathematics was what the universe was. To understand mathematics was to understand how the universe worked, which is something fitting for where we are right now. If you want to understand how the universe works, to the Greeks, you had to understand mathematics. And so the Greeks in particular were the first to develop a rigorous approach to proving results about shapes, what we would call geometry. And so this is three of the most famous of the Greek geometers, Pythagoras, Euclid, and Archimedes. And all of these guys play a role in uncovering our next slice of pie. So Pythagoras, you probably know, he dates back to about 500 BCE. He was a mathematician and a philosopher. He's probably most famous for the theorem that bears his name in the West, the Pythagorean theorem, which said on a right triangle that has sides A, B, and C, that the sums of the squares of the two sides is equal to the square on the hypotenuse, which is one of the first Greek recorded examples of a statement who related sides to areas, something that we were talking about with circles just a bit ago. Pythagoras was among a number of mathematicians who would prove little results based off of the cultures that they interacted with. They were actually traveled around the Mediterranean quite a bit. And so about 300 years later, these results would be compiled by another mathematician named Euclid into a 12-book omnibus called The Elements of Geometry. And that book encapsulated essentially every known mathematical fact that the Greeks and all of the people the Greeks had talked to, everything that they knew boiled down into 13 postulates and a couple of axioms. It's widely considered one of the most beautiful, pristine works of logic. Up until about the mid-1980s, it was the second most popular book published in the world. And it's the heart and soul of every high school geometry textbook. So thank you and or curse you, Mr. Euclid, depending on how much you like geometry. But the ideas that were in the elements were then taken by our next mathematician, Archimedes of Syracuse, and turned into something about pi. So Archimedes is an interesting guy. He was a mathematician, a physicist, an inventor, occasional streaker. He was the first person to rigorously calculate the value of the circle constant, which is what he called it. And his ideas were so fundamental that they pretty much dominated how we talked about pi for the next millennium. Can you imagine having an idea so profound that it shapes all discussion for 1,000 years? That was what Archimedes' idea, or rather three ideas were. So let me tell you what his three ideas were. So if you wanted to understand this number pi, the first thing to do is you were going to take a circle and enclose it inside and outside by the same shape. And then you could calculate the perimeters of those shapes to get a bound on pi. So in this case, imagine I've got a circle and I put a square around the circle and I put a square inside the circle. And I'm going to try to work out the perimeters of these two shapes. Now, if the circle had length 1, then its circumference would be exactly pi, because circumference is pi times the diameter. But if this length is exactly 1, then that means that the outer sides of this square are 1 by 1 by 1 by 1, and it has a perimeter of 4. So pi has to be smaller than 4, which is kind of the thought experiment that we had done before. But the shape on the inside, this little square, actually has a diagonal of length 1. And so if you know any of your high school geometry or your trigonometry, that means that the two sides are 1 over the square root of 2. I don't care if you know what that number is. I just care that it's about 0.7. And so the blue rectangle on the inside has a perimeter of 0.7 plus 0.7 plus 0.7 plus 0.7, or 2.8. The circumference of the circle is bigger than the blue perimeter and smaller than the red perimeter, which means pi has to be between 2.8 and 4. So we've got tighter bounds on it. Before we knew it was between 2 and 3. Now I can bring those two bookends closer and closer together and get a better idea of what pi is. That was idea number 1, that you could wedge a circle between two shapes, and that would wedge pi between two numbers. Big idea number 2, the more sides you used on the shape, the better those bounds would be. So if we used a 4-sided shape, a square on the inside and the outside, then we would get bounds of 2.8 and 4, and pi would nestle snugly between those. But let's erase the square and instead use hexagons, 6-sided shapes. So I'm going to stick a 6-sided shape outside the circle and a 6-sided shape inside the circle. And then go and compute perimeters one more time. So remember, our circle had diameter 1. That means, if I slice everything up evenly, that the blue shape has side length 1/2, and the red shape has side length 1 over the square root of 3. And if you want, that's an exercise for the dedicated reader to do that trigonometry. All I care about is that means if I were to go and add up the blue perimeter, I'm going to get 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 6 times. That's 3. And if I add up those red sides, I'm going to get a number who's just shy of 3.5. And so using hexagons, I get bounds of 3 and 3.5. So my window for where pi is got a little bit smaller. If I was going to go and give an estimate now, I'd say, yeah, pi's got to be on average 3 and a quarter. And that would seem consistent with our little rope experiment where I had this little extra piece floating off on the side. Big idea number 3, or sorry, big idea number 2 here. The more sides you used, the more these two perimeters would match up. And so I'm just showing an animation where I keep adding one more side to these 2 polygons. And after a while, it becomes hard to tell where the polygons end and where the circle begins. And so what Archimedes did was he used 96 sides. He put a 96-sided polygon outside the circle, a 96-sided polygon inside the circle, figured out what those perimeters were, and walked away and said, that's a good estimate for pi. How did he get a 96-sided shape in there? That was big idea number 3. He figured out how to relate the side length of one polygon to the side length of a polygon with twice as many sides. So if you knew what the sides were on a 6-sided polygon, and we just did that, you could take that information and figure out what the sides had to be on the 12-sided shape without having to do all of the other geometry in the middle. And then you could carry that over to the 24-sided object. Now, he didn't have the symbols for expressing this. He had to express this in words as a process. But if you want to see what the formula is, this is the formula. The side length on the new polygon is the square root of 2 times r squared minus 2, or r times the square root of 4r squared minus the old side length squared. And that's a mouthful. In fact, I'm having such a hard time saying it, I'm going to grab a drink of water. So give me a moment here. Now, because I'm talking about the Greeks, I would be remiss. I think they would take away my mathematical degree if I didn't at least give a Greek proof. And so I'm going to take a quick detour here. Trigger warning, this part's going to have some mathematics in it. It will look scary, but it's just the Pythagorean theorem. I promise that. And so if you don't want to do any math, just tune out for a bit until I put the detour sign back up. So how did Archimedes go and prove his big idea number 3? Well, let's start with a regular polygon. And let's say that the radius of this polygon is r, and it has a side length of s. And then we're going to double the number of sides. So we will circumscribe twice as many sides on it. And I'm going to try to figure out what the new side length is given the old side length. And so I'm just going to focus my attention on this one part of the picture right here. So let's zoom into this part, and I'll redraw it so that we can all kind of focus on what's going on. So boom, there we are. Our goal is we know R, we know S, and I want to figure out this missing side up here in the corner. And so I'm just going to focus on triangles. I'm going to focus first on this triangle right here. This triangle is a mirror image of the triangle below it, which means this corner is a right angle. That's a right triangle, and the only thing most of us remember about right triangles is Pythagorean's theorem, the Pythagorean theorem. I know the radius, or the hypotenuse. I know one of the sides. And so that means I can figure out what the missing side is. It's the square root of the hypotenuse squared minus the other side squared. So now I've got 3 sides figured out here. And now I'm just going to shift my focus to the triangle to the right. This little triangle right up here. First things first, let's figure out what this missing side is. The entire length of the picture I've drawn is r. And we just figured out that this portion underneath the white triangle was this terrible number. And so the missing length is going to be the whole distance. Take away that terrible number. And I know the numbers are getting terrible here. We've only got a couple more steps. We'll push our way through it. Now, this triangle also has a right angle in this corner, which means I'm looking at another place to do the Pythagorean theorem. I know 2 sides. I can find the hypotenuse by taking the square root of the sums of the squares of the other 2 sides. And so I get the missing side is the square root of s over 2 squared plus whatever that monster is in red squared. And if we do some algebra, this simplifies to this formula, and we're done. That was the formula that I gave for Archimedes. So thus endeth the detour. We'll go back to our regularly scheduled talk. So we've got this cool formula that allows us to find new side lengths based off of old side lengths. And so what Archimedes did was he said, all right, I'll start with a six-sided shape because I know what those side lengths are, and then I will use this formula to figure out what they were for 12 sides, for 24 sides, for 48 sides, for 96 sides. I'm not going to do that, but you are completely welcome to. This is the second activity in that packet that you can download, is a setup for this process. This is actually what's known as the process of exhaustion, which is, I can't think of a more fitting name on this particular one, but it's a chance to go through this procedure and see how Archimedes was getting the following numbers I'm about to set up. So if you're interested in that one, it takes a scientific calculator and a little bit of patience. But the short version was this: starting with the six-sided object and repeating this process 4 more times, Archimedes was able to show that, in his words, the circumference of a circle, the factor by which the circumference of a circle exceeded the diameter exceeds 3 by no more than 10 parts in 7, but no less than 10 parts in 71. In fractions, that just meant that pi was between 3 and 10^71 and 3 and 10/70. We're going to see in just a second why he didn't write them as fractions like this. The number that's on the right actually is 3 1/7 or 22/7. And this is one of the most famous estimates of pi as well. It's sometimes called the Archimedean estimate. If I were to punch these numbers into a calculator, 3 10^71 is 3.141. 3 1/7 is 3.143. And so that means pi is nestled between these two numbers, between 3.141 and 3.143, which means up to 2 decimal places, pi is 3.14. So the number that we sort of most associate with pi is actually the Greek slice. So I'm going to ask the same question I asked of the previous culture. The Greeks had a method that would allow them to get better and better fractions. They knew a theory of fractions and they knew a theory of ratios. So why didn't they ever produce a better approximation than 3 1/7? I mean, we've got decimal expansions. Why could they only get 2 decimal places? On the one hand, back off. This is an ancient culture. They were accurate to within 1/1000th of the correct value, which is fairly impressive. But maybe the real reason why is that they lacked the computational tools to get it done. They didn't have any kind of calculator. They didn't have any kind of paper to write results down on. They actually would write their results on sand tablets that you would shake off when you were done, essentially etch-a-sketches. And maybe most problematic, they were handicapped by their number system. The Greeks used the same letters, the same symbols for their letters as they used for their numbers. And this makes it really hard to do basic math. This is actually the Greek number system. Every letter in the Greek alphabet was assigned a specific value from 1 to 9, then 10 to 90, and then 100 to 900. And so if you wanted to write 2 different numbers down, 314 versus 143, to write 314 down, you would have to know the special symbol for 300, and then the special symbol for 10, and then a special symbol for 4, in this case, tau iota delta, and it didn't matter the order in which you wrote those things down. On the other hand, if you wanted to write down 143, which to you and me, we'd say, oh, those just have the same numbers, but they're in a different order. You wouldn't do that in Greek. You'd have to know the new symbol for 100, a completely different symbol for 40, and a completely different symbol for 3. In this case, rho, mu, gamma, or any combination of those. So you'd have to know 27 different symbols to simply talk about the first 1,000 numbers. And there was no idea of adding together and carrying over because the order in which you wrote the numbers down was irrelevant. It was just too difficult to use this number system to do basic or to do complicated arithmetic. Fortunately, there was a better number system out there, and that better number system would be used to find a better slice of pi. It just wasn't in Greece. It was being developed in China. And so that's where we'll go next. Part 3.14159, China. So Imperial China has been around for 2 millennia. When Emperor Qin united the warring states in 221 BCE, he began a 21-century-long rule of Imperial China, one of the longest continuous stretches of one civilization in the history of our species. Imperial China was a society that was ruled by both bureaucrats and astronomers. So people who crunched numbers for taxes, and people who crunch numbers for celestial events. And so as a result, mathematics plays a very central role in both the civil life and the spiritual life of Imperial Chinese. And so as it should be no surprise that for a culture where math plays a big role in all facets of their life, that they would be the next place for us to find a new slice of pie. They also made several advances in technology that helped them to get there. So I've illustrated 3 of them here, the abacus, paper, and movable type. So the abacus was the first calculator. It allowed complex calculations to be done with a mechanical device. Paper allowed them to write these calculations down in a permanent way. And movable type would allow them to build textbooks and then disseminate that knowledge across all of the provinces of an epic empire. In addition, they had a much better number system, much more improved than the Greek version. It's what's known as a positional number system. So where a symbol appears tells you something about the size of it. So for comparison, if I were to take the 2 numbers that we just talked about before, 314 and 143, to write 314 in Chinese, you would write it almost exactly the way you'd say it, 3 hundreds, 110, and 4. On the other hand, if you wanted to write 143, you would write that as 100, 4 tens, and 3. And so you could compare across rows to sort of see what the relative size of numbers were. You only had to know 9 digits and then a special symbol for each of what we'd sort of call powers of 10. And that made it a much more efficient number system. Whereas it required 27 symbols to do 1,000 numbers in Greek, you could get all the way up to 1 billion numbers and know no more than 16 on the Chinese side. So let's take a look at 2 Chinese mathematicians who uncovered the next slice of pie now that we have all these tools. The first is going to be Liu Hui. Liu Hui was a Chinese mathematician from about 200 or so in the Common Era, AD. And he was the first person to give a correct formula for the area of a circle. Now, I know all of you know, or in the back of your mind might remember what you think the area of a circle is, but it's not this one. According to Liu Hui, the area of a circle was 1/4 the circumference times the diameter. This is history's first correct equation for the area of a circle. And back at the beginning, when I put a pin by the area statement and said we would come back to the relationship between area, circumference, and diameter, there it is. Area is 1/4 circumference times diameter. So how did he go and show this? The idea is actually really simple. And anybody who's ever tried to put leftover pizza in Ziploc baggies has done this already. If you want to go and try it on your own, that's the 3rd of the activities that you can download off of the website. So by all means, take a look at those. But I will at least walk you through the basic idea right now. The idea is to start with a circle and to slice it like you would a pizza. And then unfurl those pieces into 2 rows and interlock them back together. So we unfurl, put them together. The resulting thing that you get is almost, but not quite, a rectangle. So what Liu Hui, who was familiar with the works of Archimedes, did is, well, if it's kind of that way for a smaller number, jack up the number of slices that you do. So if you did more and more slices, separated them and put them together, you would get shapes who looked more and more and more like a rectangle. And so he just imagined taking your pizza and slicing it up into millions of slices, which, let's be honest, would be a terrible pizza. But take those slices, rearrange them, and you'd have something that you couldn't tell wasn't a rectangle. And so let's take a look at that rectangle up close. The length of that rectangle, its length along the bottom, is formed by half of the pieces of pizza. The half of them form the bottom teeth, the other half form the top teeth. And so that means that the length of that bottom part of the rectangle is half of a circumference. The height of each of this rectangle is actually just the length of any one of those pizza slices. That would be a radius, or half of a diameter. So the length is half a circumference, the height is half a diameter, and since it's a rectangle, you can just multiply those 2 numbers together and you have area. So 1/2 circumference times 1/2 diameter gets me area being 1/4 circumference times diameter. Now, it may not look like it, but this is actually the circle equation that you know and love. And I will walk you through that. So in case you're just thinking I'm lying to you right now, let's do this quick calculation. We know that the circumference is pi times the diameter because that's what pi is. So we've just found out that the area is equal to 1/4 pi times diameter squared. Now the diameter is twice a radius. So I've got twice the radius squared, that's a 2 times an r times a 2 times an r. That means area is 1/4 pi times 4 times r squared. And now 1/4 and 4 multiplied together, they'll cancel out. And so we get that the area of a circle is pi r squared. And I have to make this joke at least once in there, so there's our square pi. But the thing that I really want to draw attention to is that this means that the area of a circle is pi over 4 times the area of the square that would be circumscribed around it. It also means that the circumference is pi over 4 times the perimeter of that very same square. That was what the Egyptians said. So if I had a chance to rename everything, I would tacitly say that we done screwed up in history, and we should have been focusing on the number pi over 4. That was the thing that united everything together. But yeah, I don't get to say how history works. But one of the things you do if you learn a little bit more about the history of pi is that you'll often see pi over 4 is the number that cultures were approximating. And this is the reason why. It was the common feature that reunited areas and perimeters. So that idea right there, that the area of a circle was pi over 4 times the square of the diameter, was the idea that our next Chinese mathematician used. This is Zhu Shangji. He was about 450 or so in the Common Era, and he took this idea and he ran with it. He went and repeated the Archimedean polygon process, but he made 2 major changes to Archimedes. Change number 1 was that he found out that if you use the area description rather than the perimeter description, the areas of the inside and outside polygons gave better approximations of pi over 4 than the perimeters did. And so he said, let's just do areas from now on. So he used areas in his calculation. The other major change was that he used a lot more sides. A lot more sides. Almost 13,000 more sides. He used a 12,888 sided polygon as his final calculation. And I do not have a worksheet for that one for you to play around with. If you want to understand what exhaustion is, it's that calculation right there. But the upshot of the calculation, using a 12,288 sided polygon, Zhu Shangji showed that pi was larger than 3.1415926, but smaller than 3.1415927. And so 3.14159, that's a good description of pi. Now, rather than try to make people remember that by itself, he came up with a mnemonic. He said, pi is approximately 113355. So just list all of the odd numbers, the first 3 odd numbers twice, 113355. Now, if you look at that, that's a terrible approximation of pi. It doesn't even have a 3 in the front part. But it's only terrible if you write it like that. What Zhu Shangji said is, no, it's a fraction. Take the 355 and put it on the top and the 113 on the bottom. And 355 over 113 is 3.1415929, actually. So it's a number who is about 3/100 millionths off from the correct value of pi. And so this value right here, 3.14159, is what's known historically as the Chinese estimate, the Chinese slice of pi. And there would never be a better approximation for the value of pi that anyone would ever get by using the Archimedean idea of polygons anymore. And so 3.14159, excellent slice of pi, but I've got more digits still. So how do you get more digits of pi if I just told you that humanity never got any better than this by doing the polygon trick? Is it possible to find the digits of pi, but not from estimating areas or circumferences, but from analyzing just the number pi itself? And amazingly, the answer is yes. And to figure out how to do that, it'd take another 1,000 years, and we'd have to go to India. So part 3.14159.265, let's go to medieval India. So India, the Punjab continent, is a mix of a number of different cultures. By the time we get to 1400 in the Common Era, this is the late medieval period in India, and it was marked by a synthesis of cultures interacting with each other and religions bustling with each other. There was Jainism and Hinduism, Buddhism and Islam, all sort of vying for ideas, translating notions back and forth. And because you had all these societies and all these cultures interacting, there was a synthesis of their ideas that sparked advancements in math and science along with it. Now, math in India goes back quite a bit. The earliest traces of mathematics in India go back to Vedic Hindu culture, which is around the same time as the Fertile Crescent. But it hit its stride in what's called the Kerala school. And Kerala is actually that temple that I showed you on the slide immediately there. This was a place where Indian scholars would come to develop new mathematical tools and techniques, often in the service of religion and often just in the service of poetry, which is a weird idea. And I'll get to that in just a second. So let me talk about some of the tools and techniques that these Indian scholars came up with. So number one tool, they built an even more efficient number system than the Chinese did. It dates back to the early Vedic Hindus. So this is the symbols that they used there. I'm not going to put a translation key here because by the time we get to the late medieval period, those symbols had morphed into things we're a little bit more familiar with. These are the precursors of the modern Hindu Arabic numbers that we use today. Pretty much 4 got moved over from 5, and then they just made some brand new symbol for 5. But other than that, they are pretty spot on. So when you start reading mathematics that comes from the Kerala school, it looks like how we would write numbers down. The next big idea was something called trigonometry, which we could say is the systematic study of lengths and angles, which is a measurement of how far apart 2 lines are. The 2 most important concepts in trigonometry are something called the sine and cosine. This isn't a trig class, so I'm just going to give you a very bare bones description. If you had, say, a right triangle, and you had an angle in one of those corners that you decide, I want to pay attention to this angle X, then the length of the side opposite that angle is called the sine of the angle. And the length of the side that rests against it is called the cosine, or the complementary sign, because it's the sign of the complementary angle. This is not quite how sine and cosine are defined in a modern trigonometry setting, but it is how the Indians defined them. Some of the major changes were that we abbreviated cosine into just cos, and we always now assume that these are ratios of these sides over the hypotenuse. But what I'm about to say would make sense under any of these descriptions. The third big idea was that Indian mathematicians stopped being afraid of the infinite. Whereas most cultures would say, oh, infinity is something to be scared. You could never get to an infinity. The Indians of the Kerala school were like, bring it. I'm going to make infinity something that I can tame. And so they built a lot of mathematics that just embraced infinite ideas. And so one person who tied all of these together, the new number system, trigonometry, and an embrace of the infinite, was the Indian mathematician Madhvada, who was the founder of the Kerala school. And this is about 1400 or so in the Common Era. So the result that I want to point out in the story of pi is this result. Madhvada used the Archimedean process to find a way to compute the length of a circular sector given its angle. And if you're not down with your geometry, I've shown a helpful piece of pi up there. What I mean is I can figure out how long the crust is if I know how wide the pie slice is. And so he gave a formula for that. Now, because he was an Indian scholar who was part of this long line from the Vedic people, he didn't write things down in formulas. He wrote things down in poems. And so he described this by a poem. And this was the poem. The first term is the product of the sine and the cosine, or the sine and the radius divided by the cosine. The succeeding term is produced by iteratively multiplying the square of the sine and dividing by the square of the cosine. All of the terms are then divided by the odd numbers 1, 3, 5, and the arc is found by adding the terms of odd rank and subtracting those of even rank. It loses something in the translation from ancient Hindi, sorry. I'm not going to try to prove this, but I do want to understand what the poem says. So sine and cosine we just talked about, that would refer to this vertical height and this horizontal height of the implied triangle in this piece of pi. And so let's focus on the other pieces of this. The first term is the product of the sine and the radius divided by the cosine. So that would be r times the sine of the angle divided by the cosine. Each succeeding term is found by multiplying by the square of the sine and dividing by the square of the cosine. So I'd stick 2 sines on the top and then 2 sines of the cosine, then 2 sines again, 2 cosines again, 2 sines again, 2 cosines again, and I'd have this list. Then all of the terms are divided by the odd numbers. So I'm going to stick a 1 and a 3 and a 5 and a 7 in those denominators. And then the arc is found by adding the terms of odd rank and subtracting those of even rank. So I'm going to go add, then subtract, then add, then subtract, then add, then subtract. There's a rhythm hidden inside here. And that's what the poem says. If you want to figure out the arc on the left, then this infinite sum on the right tells it to you exactly. Now, let's just do a simple case. What happens if the radius is 1 and the angle is 45 degrees? Well, if I know exactly the radius and the angle, that arc is really easy to draw. I'm going to move over some whiteboard here. I've got a radius of 1 and an angle of 45 degrees. I've drawn you 1/8 of a full circle. The diameter would be 2, so the circumference would be 2 pi, and this would be 1/8 of that. And so 2 pi divided by 8 is pi over 4, which was the number I said was important. Nope, we got pi over 4. Let's go take a look at the right-hand side. I've said that the radius is 1 and the angle is 45 degrees. If you've got a right triangle with one angle being 45, that means that the other angle is 45. And that means that these two sides are exactly the same length. And so the blue side is the sine and the purple side is the cosine. They're going to cancel out in this fraction. And in this fraction, and in this fraction, and in this fraction, all the way down the line. And so you're just going to have r's, which are 1 in the top, and the numbers 1, 3, 5, 7 in the bottom. And so what we have here is the Indian slice of pi, but that's actually kind of a misnomer because this is not a slice. This is actually pi. This is history's first exact formula for the value pi. Now, I could never add up everything on it, but I can build approximations not by trying to maximize it or minimize it between two other shapes, but by just going out farther and farther in this one formula. If I have something that's not accurate enough, I don't have to go back to the drawing board and start with new circles or new polygons. I just add the next term over and over and over again. Everything I'd ever need to know about pi is in this one equation. I will point out that it's exceedingly inefficient. To get to 3.14 as an approximation, you have to add, I think, the first 200 terms. And so this isn't the be-all, end-all. And what would happen is the ideas that the CRADLE school developed would be refined over the next few centuries with the help of the Enlightenment scholars from Europe into a whole new branch of mathematics that dealt with infinite sums and infinite products called calculus. And I'm not even going to try to talk about what calculus is, other than to show you some of the beautiful equations that come out of this in describing pi. So instead of describing pi over 4 as 1, take away a third, add a fifth, take away a seventh, add a ninth, take away 11th, you could write it as different kinds of expressions. So it's 3/4 with adjusting terms that are products of 3 consecutive numbers, added, subtracted, added, subtracted. You could write versions that had squares of numbers and roots in them. Pi is the square root of 6 divided by 1 squared, plus 6 divided by 2 squared, plus 6 divided by 3 squared, plus 6 divided by 4 squared. These nice simple formulas. They could be written as products. Pi over 2 could be written as 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5, all the way down the line. They could be written as these cascading steps. They could be written as complicated formulas. But the upshot was that these expressions for pi, mathematicians were able to show that it was irrational, transcendental, and in the end, it was a knowable thing. So this would be the place where I would usually end, except I did promise I was going to try to teach you 16 digits of pi. And so I know what you're saying right now. This has been a big romp. I hear you. You're saying, God, I need a drink. Alcoholic, of course, after all these lectures involving radical equations and pi. In fact, it might make you feel better to say that. So I'm going to put the words up here, and I'd have all of you at home chant at your computer with me. God, I need a drink. Alcoholic, of course, after all these lectures involving radical equations and pi. One more time. God, I need a drink. Alcoholic, of course, after all these lectures involving radical equations and pi. God, I need a drink. Alcoholic, of course, after all these lectures involving radical equations and pi. This little ditty is what's called a cadaic. It's an English sentence that encodes the number of letters in each word, encodes the corresponding digits of a decimal expansion of pi. I've actually been giving you a whole bunch of them. Every one of the little title placards has had a little statement at the bottom. Why? May I draw a circle? Wow, I made a great discovery. May I have a month professor to figure these? Each of which are themselves little cadaics. The cadaic I gave at the beginning of this, the God, I need a drink, is actually part of a very old formula that encoded 23 digits of pi. And I happen to think this is fascinating, these poems that encode this. Maybe I don't have this memorized, but it's a fantastic one. Someone went and took Edgar Allan Poe's The Raven and turned it into a cadaic, starting with his name at the very, very top. And I'm not going to read this other than to point out that this isn't even the end of it. It's actually the first chapter of a 14-chapter novel in which a person realizes, it's all Cadaic, they're each digit of pi, but it's about a person who realizes that his world's been subtly changed by the digits of pi. You can read it at www.cadaic.net. But it's also a place at which I'm going to end talking about this, because we've come full circle. We started at the very beginning talking about this object that played an important role in religion and art. And then mathematicians went to talk about it. And now we've got the very, very end, and we have artists who are telling mathematicians how to memorize these things. So on this 2021 Pi Day, take a moment to recite your favorite Cadaic and reflect on the epic history of this number and how it's changed our perceptions of mathematics and our understanding of how the world has been changed by the digits of this number. So thank you, everybody, for listening to me. Thank you for the Sanford Lab for having me come here, and for School of Mines for paying me to talk about stuff like this. Thanks.
Well, we're going to take a couple questions while we have you up there. Can you hear me all right? Am I on? Great. Okay, so we have one question from the Zoom webinar. And apparently this is something that has been bothering our viewers since they were a little kid about pi. He says, since the exact value of pi can never be calculated, does it mean that we are not able to find the accurate area or circumference of a circle? And this is from a School of Mines engineer.
So there's two answers to that question. Answer number one is if you mean the symbolic answer, well, I have this symbolic description. I have this number which I can write out to any level of decimal precision I would like. And so, you know, the fact that I might not be able to write it out in a finite number of steps doesn't really so much faze me. If I have like the number, you know, 1/3, that's 0.333333. Something being infinitely long doesn't mean we don't know it exactly. It just means it's hard to write down. And so on the one hand, yeah, we can talk about what the area or the circumference of a circle is exactly. It just refines the symbol set that we have to use to talk about it. Our current symbol set is sometimes not well defined enough to handle that infinite stretch, but we have other ways of talking about it that do make it precise. The second answer, though, is if you're talking about an honest to God circle like this thing in the real world, we could never measure this thing exactly anyway. No matter how much I try to measure across the length here, I'm always going to have to eyeball. It falls between two different tick marks on something. I'm always going to have some level of error in how I measure it. But what these slices of pi say is we can know pi to such decimal precision that the only thing that will cause errors in our calculations are the errors in the measurements first. And I happen to think that's kind of a nice thing. The only way we can screw up our formulas is in user error. At least the math will work itself just fine.
Great. We have another question from Facebook asking, what is a transcendental number?
Oh, all right. So let me start with irrational numbers first. Irrational numbers are numbers that can't be expressed as fractions. And so that means they're numbers whose decimal expansions never repeat and never terminate. And so essentially what an irrational number is it's a statement about what you can't be. To be irrational means you cannot be a fraction. So transcendental is a kind of number that's, again, quantified by what it can't be. And so what a transcendental, or what a non-transcendental number is a number that you could get by solving a polynomial equation. So like the number 4, I could get by solving the equation x minus 4 equals 0. And the number square root of 2, I could get by solving the equation x squared minus 2 equals 0. So an awful lot of irrational numbers can be expressed as solutions to polynomials. To be transcendental means pi cannot be written this way. There's no equation out there that I could write down, a polynomial equation that I could write down with integer coefficients where if I were to solve it, pi would fall out of that. So what it says is that pi is not a number that comes from algebra alone. It's really a number that comes out of geometry. And I can only articulate it by these geometric descriptions.
Great. And this might not be something you know, but what is the furthest digit of pi that has ever been calculated, even with a computer?
So I don't know, because that value changes almost daily anymore. And there's two answers to that one. I think when it comes to the decimal expansion of pi, so the 3.14 version that we're used to, we're in the, I think we're into the high millions on that. Another way of describing pi, though, is by it's what's called its binary expansion. So how to write it in terms of zeros and ones. And that's usually when you hear about a computer talking about, oh, this computer has figured out pi to this ungodly amount. They're usually talking about the binary expansion, the 0-1 expansion, which is a little bit easier for computers to do. And we're in, I think, the low trillions on the binary expansions of pi. So when someone says my computer's now figured out like the 10 billionth digit of pi, and you ask them what is it, they're always going to say 0 or 1 because they're actually using a different number system to talk about their pi.
Right, and so you might have touched on this with that answer with binary versus our regular system, but could we, with a better number system, get closer to the exact number of pi?
So, the answer to that one is I don't know. Every time we've had a new advancement number system, it's come with a profound change in how we think about how we organize or structure number. And so going from simple pictographs for certain kinds of grouping to a positional number system where we have a set of symbols that essentially help us count on our fingers, and then we group them by certain powers. So a based number system is a positional based number system. There might be other number systems out there that just require a profoundly different way of organizing how we quantify things. One of the ways that we can quantify numbers is what are called imaginary numbers or complex numbers. So if you've ever heard the imaginary number, the square root of -1, that's a number system where your numbers aren't in a line anymore, but they're arrayed out in a plane. And so you can describe pi with complex numbers as sort of specific lengths between certain numbers in this complex plane. And so you can get very different kinds of descriptions of this value pi by sort of changing how you decide what a number is or isn't. And so there might very well be number systems out there that allow us to describe a much wider array of numbers than the ones that we're used to. But I don't know what they are, unfortunately. I do know that there's something called the nimbers, which is a weird number system that allows you to talk about the infinite, the very, very big and the very, very tiny what would be called limits in a calculus class, and you can actually turn them into special kind of numbers that somehow are wedged between 0 and the positives and at the very, very end of the number line. They don't help us at all for talking about pi, but it's a wildly different number system that allows us to talk about the infinitely big and the infinitely small. And since pi, at least in our decimal expansions, is only known by these infinite formulas, maybe that's a number system that might give us some better way of talking about it.
Great, and one last question. Can you recommend a book for non-mathematicians that discusses math in the way you just have, math and its history and significance for our culture and humanity?
I can give you two. So one of them, there's oh, now I got to remember what they're called though. So the author is Bill Dunham, and I'm having a brain fart on what it's called right now. I want to say something like called like a mathematical voyage, but it's a book that has 26 chapters, and each chapter is just a letter of the alphabet. And so each one of the chapters, mathematical universe. Yeah. There we go. Mathematical Universe by Bill Dunham. 26 chapters, each of which start off with a letter in the alphabet, and it's just storytelling that talks about math from different cultures, different kinds of ideas. It doesn't require that you have anything much more than maybe a high school algebra experience and the joy of just learning about these things. And Bill Dunham he's a wonderful expositor. He's one of my heroes. I've gotten to actually listen to him talk before and have him shoot down an idea of mine in a conference. He's fantastic guy. Can't recommend his books enough. There's another book called The Art of Mathematics by Jerry King. And The Art of Mathematics is essentially, the whole premise of this book is that you've probably been sold mathematics as a tool for solving real world problems. You know, that it's how we do science. Mathematics is nothing more than a telescope or an atom smasher. It's a tool for science. And the whole idea of The Art of Mathematics is there's an entirely different way to view mathematics as a creative art, as a sculpture or a music for just your mind, and that there's an aesthetic to it. And so it goes through a lot of interesting examples from history. It draws on examples from history of math, but also examples from the history of art, and sort of shows that there's this great cohesion between them. I myself started out as an art major when I was in college, and I graduated with a degree in mathematics, but I always told people I never changed my major. I only changed my medium. I started making art and music that you could see only in your head. And there's this, so it's a really nice, great little book, light on terrible mathematics and big on the idea that if you like art, if you like music, if you like humanities more than you like sciences, then there's no reason you shouldn't like mathematics. In fact, he gives this really nice metaphor. He says, you can imagine all of the disciplines out there. So disciplines on, say, this side are the more sciencey ones. So maybe there's chemistry here, and there's physics over here, and then there's like theoretical physics, and sort of the most mathy science would just be math over here. But then on this side, you have all of the humanities. So you have, your arts and your literatures, your social sciences. And as you move farther and farther to the right, you have more and more pure forms of art. So pure forms of music, pure forms of painting. And at the very, very end, you'd have just the understanding of the purest shapes out there, which would also be math. And so instead of thinking of human disciplines as this line, and this actually is a nice tie together for all these things, you can think of mathematics as the point who ties these two disciplines together. It's the most scientific of the sciences, but it's also the most artistic of the arts. It is the only art that everybody on this planet has ever agreed on. We don't agree on politics. We don't agree on our gods. We don't agree on what counts as good music, what counts as good stories, what counts as good clothes. But we all agree on how we're supposed to group things, how those things fit together, what things make sense for us when we want to talk about the world in a way that would make sense to our children. It's the one language we agree on. And if you view it from the lens of that it's this human language, it's the oldest art we have on this planet. And it's one that you get to work on and contribute to every day, which is kind of cool. And then the fact that it's useful just means you get paid. So, it's art that I get paid to do.
Terrific. So, well, thank you so much. And
thank you.
That was a great Q&A session.
Somewhere in here I have my mask.
Sure. We'll just switch places in a second.
There it is. So I go on. Follow good social distancing guidelines. Put on my mask. Thank you.
Thank you very much. Awesome. Well, that's a great presentation. And I do want to point out that we have a gift for you. We have this photo of the Ross head frame. It's kind of looking out over Kurt Canyon, and it's very beautiful snow dusted, and that's pretty pertinent for what I think we're getting this weekend, as well as a Sanford Lab pin. So that's for you. I'll give that to you in a minute. And like Dr. Kowalski said, we have 3 downloadable activities that you can do to kind of practice all of this yourself on our website. So just go to the Pi Day event on our website, and they'll be down there for download. You can also find that link in the chat before you leave Zoom and the Facebook comments before you leave the video. I'll end this talk with a reminder to join us on Thursday, April 8th for a live virtual tour of the Ross Hoist Room. That will be with Sanford Lab Executive Director Mike Headley and Fermilab Lead Engineer Josh Wilhite. They're going to be giving an update on the Sanford Lab facility and a little bit on the LBNF Dune project. So you can watch for that information on our website and on our social media channels. I also want to give a big thank you again to our Deep Talk sponsors and the awesome Sanford Lab communications team that makes this possible. A recording of this talk will be shared on Facebook, Vimeo, and YouTube, so feel free to share it with a friend who missed the event. When you leave the Zoom webinar, you'll be given the opportunity to take a survey about your Deep Talks experience. So please leave us some feedback so we can keep making these events better and better. Thank you so much for joining us tonight, and we will see you next month on April 8th.
Aaron, can we post the names of those 2 books on our
Yes.
page?
Yeah, we'll definitely get the information about those 2 recommended books on our social media and our website.